As we saw, most elements can come in different varieties, different versions in the same place, called isotopes. Amazingly, some elements can arrange their molecules in different shapes, and those different shapes will produce very different results. The same atom in a different shape can completely change the characteristics of those elements. These different shapes are called allotropes, which means, different shape. The most famous allotrope example is carbon. Carbon not only bonds with other atoms to form more compounds than all the other elements put together, but it also has more known allotropes than all other elements, 8 so far. Here are the most famous different shapes carbon takes. Graphite. Graphite is the most abundant and common form of carbon. Notice how the atoms are layered in graphite. The word graphite means to draw or write, like in graphics, because graphite is used in pencils. Graphite can be extremely strong and heat-resistant. Carbon fibers in airplane parts, golf clubs, and heat-deflecting tile shields for spacecraft are examples. Graphite, a carbon allotrope, a different shape. Diamond. Diamond is the most well-known carbon allotrope. Exact same carbon atoms as graphite, but arranged in this tight bonding network. No known naturally occurring substance can scratch a diamond. Molecule arrangement is why graphite and diamond are exactly the same, but so different. Diamond, a carbon allotrope. Amorphous. Soot and coal are often called amorphous carbon. Coal, a carbon allotrope. Fullerenes. In 1985, a brand new allotrope shape of carbon was discovered. This shape is called fullerenes, or buckyballs, named after Richard Buckminster Fuller, an architect who was known for the design of geodesic domes, which resemble this allotrope in their appearance. This closed shell allotrope of carbon has produced substances 20 times stronger than steel with half the weight of aluminum. An entirely new branch of chemistry developed with the discovery of this new allotrope, this new shape. Fullerenes, a carbon allotrope. Besides carbon, about a dozen elements form allotropes, including ozone, the famous allotrope of oxygen. As we know, each element has a name and an abbreviated chemical symbol that goes with that name. Hydrogen, chlorine, argon, and lead, or H, Cl, Ar, and Pb. Fortunately, there's only about 100 elements and abbreviated symbols to deal with. Likewise, each molecule has a name, but there are millions of named compounds and millions more discovered and named every year. In fact, the American Chemical Society recently announced the naming of the 50 millionth substance. It took until 1990 to reach the 10 millionth chemical. 18 years later, chemical substance number 40 million was named. Only 9 months after that, they hit number 50 million. This exponential growth in chemical substances means that a new chemical is now discovered and named every 2.5 seconds. In order to name each of these molecules, a series of very complex and elaborate rules has developed, rules carefully managed by IUPAC. The complete system is an enormous topic, and it usually takes chemistry students several months to really master it. But we can hardly talk about chemistry without mentioning some of the common chemistry names and a few of the rules that make up what is known as chemical nomenclature. And just what does nomenclature mean? The word comes from Rome and the Roman nomenclator. The nomenclator had the job of whispering the names of people into his boss's ear as they approached him at parties and political events. This is Senator Cassius and his wife Drusilla. Nomenclator literally means the name caller. So, chemical nomenclature is the art of giving chemicals their names. With a single element, there's just one step. You simply have the name of the element: copper, hydrogen, iron. The next simplest is two elements forming a simple covalent compound. And since there are two elements, they get two names. First, write the name of the two elements in their family order as they appear on the table, numbers 1 through 8. For example, hydrogen, then oxygen, because hydrogen is in group 1 and oxygen is in group 6. Carbon, oxygen. Gallium, arsenic. Then you cut off the very ending of the second element and add IDE, which is the Latin meaning belonging to. Hydrogen-oxygen becomes hydrogen oxide, oxygen belonging to hydrogen. Carbon-oxygen is carbon oxide, oxygen belonging to carbon. Then, if we want to abbreviate these chemical formulas, we do it like this. Hydrogen oxide, hydrogen is H, oxygen is O, HO. Gallium arsenide, gallium is Ga, arsenic is As, GaAs. These are the chemical names. These are the chemical abbreviations or formulas of those names. Often there's more than one of the same atom in a molecule, like 2 hydrogens and 1 oxygen. And since the English words 1, 2, and 3 simply won't do, scientists use the Greek and Latin prefixes to name those numbers. And here they are. 1 is mono, like a monorail is a train on one rail. 2 is di. A dialogue is a conversation between two people. 3 is tri, like in tricycle, 3 wheels. 4 is tetra, like tetragon, a 4-sided figure. 5 is penta, like the pentagon is a building with 5 sides. 6 is hexa, like a hex-head bolt has 6 sides. 7 is hepta, and is pretty uncommon, but a heptad is 7 people. 8 is octa, like an octopus has 8 arms. 9 is nona, and is not to be confused with the double N nonna, which is Italian for grandmother. 10 is deca, like a decade is 10 years. This element has 1 carbon and 2 oxygen atoms. It becomes carbon dioxide. Its chemical formula is 1 carbon, C, and 2 oxygens, O, with a little subscripted 2 at the bottom of the O, CO2. Carbon monoxide, 1 carbon and 1 oxygen atom. Its formula is CO since you don't write the number 1. You can actually make good guesses as to what the chemical name is just by looking at the formula. Sulfur dioxide, SO2. 1 atom of sulfur, 2 atoms of oxygen. Dinitrogen monoxide, N2O. 2 atoms of nitrogen, 1 atom of oxygen. Sulfur hexafluoride, SF6. 1 sulfur, 6 fluorine atoms. Dinitrogen pentoxide, N2O5. 2 nitrogen atoms, 5 oxygen atoms. And P4S10 is called tetraphosphorus decasulfide. Those are the rules for simple covalent compounds, compounds with no metals in them. If there is a metal, it's called an ionic compound, a positive cation metal electrically attracted to a negative anion from the nonmetals. Although many use the same method as covalent compounds, like sodium chloride, others can be quite complex, and tables are often used to keep the nomenclature straight for ionic compounds. Beside their official names, many chemicals have non-scientific or everyday names that we know them by. For example, NH3 is nitrogen trihydrogen or hydrogen nitride, but we always just call it ammonia because in the ancient temple to Jupiter Ammon, they would burn camel dung for light and heat. The soot deposited little white crystals on the walls, which they called salt of Ammon. O3 is trioxygen, but we call it ozone. NaCl, sodium chloride, is table salt. H2O2, dihydrogen dioxide, also known simply as HO, is hydrogen peroxide. MgHO2, magnesium hydroxide, is milk of magnesia. N2O, dinitrogen monoxide, is known as nitrous oxide or laughing gas. NaHCO3 is sodium hydrogen carbonate, which we know as baking soda. And finally, there is the dangerous dihydrogen monoxide. Dihydrogen monoxide is the major component of acid rain. It contributes to the greenhouse effect, can cause severe burns, and badly advances the erosion of natural landscapes. In spite of these potential hazards, dihydrogen monoxide is widely used as an industrial solvent in the distribution of pesticides and is now a major additive in many processed foods. Dihydrogen, H2, monoxide, O. Dihydrogen monoxide, more commonly known as water. Water is the major component of acid rain. Water contributes to the greenhouse effect. Water can cause severe burns. And water badly advances the erosion of natural landscapes. In spite of these potential hazards, water is widely used as an industrial solvent, and water is used in the distribution of pesticides. And now, water is a major additive in many processed foods. Dihydrogen monoxide, water. That gives you a flavor of how some of the many, many molecules are named. But before we leave this section, there's one other molecule we'd like to look at: minerals. Generally, if you are a molecule substance that is a solid, not man-made, is not living, and has a predictable composition and crystal structure, you get to be a mineral? So, by that definition, some of the solid elements on the periodic table are minerals, and that includes gold, silver, and sulfur. Rocks, on the other hand, are combinations of minerals. Minerals are the building blocks of rocks. There are about 4,000 known minerals, 98% of which are rare or extremely rare, and about 100 of them are common. But some minerals are common enough and rare enough and wonderful enough that we call them gemstones. Silicon dioxide, known as quartz. And the purple variety of quartz called amethyst. Beryllium aluminum silicate, or emerald. Beryllium aluminum silicate, the blue transparent beryl known as aquamarine. Magnesium aluminum silicate, the red garnet. Hydrated copper aluminum, turquoise. Magnesium iron silicate, known as peridot. Aluminum oxide with chromium, commonly called ruby. Hydrated silicon dioxide, opal. Aluminum oxide, in a color other than red, becomes sapphire. Aluminum silicate fluoride hydroxide, or topaz. Carbon crystal, the mineral known as diamond.